Hello everyone, welcome to the 14th episode of Math and Beyond and this podcast. So I have had some time off from school and the podcast in general because I terminated my exam session at the end of May, and so I gave myself some time off to enjoy the good weather that these days and the last 10 days approximately has been found in Amsterdam. And today we are going to talk about quantum computing and DNA related computing and processes that we can find within computing systems. And we are going to talk with Manish Gupta. I will now send him the invite, and I will see you shortly. Hi, hello, Manish.
Hello, how are you?
Hi, I'm doing fine. What about you?
Yeah, I'm doing good.
Okay, great. Where are you?
Pardon?
Where are you?
Sorry, I can't hear you. I think there's some noise coming here. Yeah.
Okay, can you hear me? Can you hear me now?
Yeah. Now I can hear you. Yes.
Okay, great. Where are you?
Pardon?
Where are you?
Yeah, I'm in Gandhinagar, Gujarat right now, India.
Okay. Yeah, I gave a small introduction about the topic of today. We're going to talk about quantum computing first, and then we are going to span onto DNA computing. So I think that is a very exciting topic to talk about these days. So I think we can jump into it. And I would like to ask you very broadly and very generally, what is meant by quantum computing? Because we know that we have a theory of physics, which has the name of quantum, which is quantum mechanics, which deals with the tiniest that we can find on Earth, in the universe, and related. So what is meant with quantum computing, and where does quantum mechanics, kicks in quantum computing?
Okay. So I think, first of all, I just wanted to tell you that the computers that we use today, they are based on classical physics, where basically we store information on the charge of an electron, right? So the whole electronics is based on that. And when we go to the quantum mechanics, so basically these are based on classical physics. I mean, classical physics is sufficient to do computation here, what the computer that we use. In case of quantum computers, so the physics is now quantum physics. So essentially, now we can actually store information on the spin of the electron. Okay, for example. So, it is much more powerful in a sense. So now electronics is going to become spintronics. Okay, it's kind of generalization. And I think from the computing perspective, or especially mathematically, I would say that just like that, we have a real line in mathematics, and we extend real line to complex frame, right? And then we can solve any polynomial. In that sense, if you give an analogy, so we can say that classical computing is extended to quantum computing in that sense. Okay, so now we can do more things. So basically, why quantum computing started? I mean, I think, as you know, that in 1900 there was in fact 1900 is a year which was very important. In the International Congress of Mathematicians, David Hilbert actually posed those 23 problems. And you might be remembering that famous lecture by David Hilbert, and asking, and he was saying that mankind will remember Hilbert for these 23 problems, which are unsolved problems. So one of them was decision problem, because Hilbert used to prove certain things, and and he thought that maybe there is a systematic mechanical procedure through which one can prove things in mathematics. Right? So he asked this question, and the answer to this question was given by two people in negative, and one of them was Alan Turing, who actually tried to construct a pen and paper computer, and he said that, I mean, he demonstrated that there is a problem which cannot be solved by that machine. Now it is known as Turing machine, which is the theoretical analog of our computer that we use today. Now, after this, at the same time, in 1900, there was a, Max Planck, actually, he asked this question whether, any glowing body changes temperature, its color changes basically when the temperature increases. Why is that? And the answer was based on the assumption that this energy comes in the discrete form of quantities known as quanta, and that was the birth of quantum physics in 1900. And then after that, many scientists worked on that. In fact, Feynman actually asked many interesting questions once the quantum physics was discovered. So maybe, I mean, in that famous lecture, there's plenty of room at the bottom at Caltech. He actually, talked about that maybe we can build a quantum computer based on basically quantum physics principles. And it was just an idea, at that point of time. Not many things were clear. And this idea of Alan Turing came in 1936. So it took 36 years to actually describe computer theoretically. And then people started asking several questions. Can we make quantum Turing machine as such? And I think it took another several years, in fact, a couple of decades. So finally, in 1980, 1980 actually, the first time someone proposed that we can build a quantum Turing machine, so analog of Turing machine based on quantum physics. But it was not really truly quantum Turing machine because many of its operations were still classical. So finally, in 1985, David actually gave a true quantum Turing machine. So essentially, from computing perspective, because as I mentioned, mathematicians can look at computers and they can compare computers in the form of Turing machine. So classical Turing machine was extended to quantum Turing machine in 1985. And since then, people started asking questions, okay, if there is a quantum Turing machine, what kind of problems it can solve? Can it solve problems which cannot be solved by classical Turing machine? And many, theoretical computer scientists started looking into this problem, and then they arrived at different problems they picked up, and they showed that in some cases, problem can be solved by quantum Turing machine. I mean, of course, but that can also be solved by probabilistic Turing machine, which was another generation of Turing machine. And finally, there was a clear-cut separation that there are problems which can be solved by quantum Turing machine, but cannot be solved by classical Turing machine. And that was a clear separation. This is in the years, 90s, towards the late 80s and early 90s. And I think that was a very, very important era when Simmons' algorithm came into picture in 1992 or 93, I guess. And finally, in 1994, a remarkable discovery was done by Peter Shor. You might be knowing Peter Shor is a great mathematician who picked two very popular problems, which, in mathematics, on which cryptography was built, actually, especially the RSA crypto system, which was based on integer factorization problem. And we know that integer factorization is a very difficult problem. As you can, there was an estimate by, UC Berkeley professor that Umesh Vazirani, that if we have a 2000 digit number, if we want to factor that, it will take, and if you assume that every particle in the universe is a classical computer and they compute for the entire life of the universe, that would be insufficient to factor a 2000 digit number. Such a difficult problem it is. And that's why RSA crypto system was built on the top of it. So similarly, and there was another problem, discrete log problem. So when we take any discrete structure like a group, right, and if you solve discrete log problem in that group, it was a very difficult problem for the classical computers. So Peter Shor discovered polynomial time algorithms for both of these problems in 1994. It's a very seminal paper, and which is, I mean, it was based on quantum Fourier transform, the ideas from quantum Fourier transform, which is generalization of Fourier transform, and actually that led to a lot of discoveries, and a lot of people started discovering new algorithms or for problems that can be solved by quantum computers and cannot be solved by classical computers. A lot of, for example, Grover search algorithm. So we know that if there are n objects, we can find one object in the worst case complexity of order of n. We need to look at each and every object. In a quantum computer, by the way, you can do it in the order of a square root of n. It's clear-cut improvement on the classical search with quantum search, right? So, so these are some of these discoveries led to, other people to discover the hardware. In fact, there was first company, D-Wave, which actually tried to get the quantum computer, and it's a Canadian company actually. And after that, but then IBM actually did one experiment. They implemented the factorization of 15 is equal to 3 into 5 using fluorine molecule. So, it's NMR based quantum computers, but it was very limited. The approach was very limited. You cannot scale these approaches. And, so finally, there was a period when there was not much movement going on in quantum computers. Finally, I think, in the mid 2000s, 2004, 2005, I think 2006, when many companies, the industrial companies started coming into the picture, for example, Google, IBM, and other companies. And because of involvement of the industry, actually, again, a lot more things have started happening in the hardware sector as well. And nowadays, a lot of superconducting qubits, people are trying to build computers based on that. And, many, I think, more than 60, 70 companies are there which are working in quantum computing these days. And some of the problems that quantum computer can solve are, as I mentioned, people have listed a lot of interesting problems. But I think a very hot area these days is quantum machine learning. I think that machine learning and AI is anyway is a quite buzzword. And now people believe that quantum AI or quantum machine learning will be able to solve many interesting problems. And I think there are many banks, for example, JP Morgan Chase Bank in US, they have a Center for Emerging Technologies on quantum computing. So they want to work to what is now known as quantum finance. So, a lot of companies are focusing on that in financial domain, a lot of interesting problems can be solved by quantum computing because obviously quantum computers are better. Okay. Now, one can actually compare that, in our classical computer, at any point, the smallest unit of information is bit, either 0 or 1. Okay. So if there is a 3-bit register, so at each point, there is either 0 or 1, right? So that is the case with bit. But in case of qubit, which is the smallest information, quantum information, so basically there we have qubits. So qubit you can think of a unit sphere, and there is a vector, moving in that unit sphere. And so basically, it is a Hilbert space mathematically if we talk about. And whenever we are reading it, it will collapse in one of the basis state, ground state or the excited state, you can think of. So if you are implementing in the form of hydrogen atom, for example, qubit, you can think like that also. So basically, when we do the measurement with certain probabilities, the qubit state will collapse into one of the state. Okay, so this is the key idea. So basically, you design an algorithm, you give input to the quantum computer, and then it will evolve through unitary evolution, and then basically it will give rise to interesting, observation. So it will finally you do the measurement to read the things, what is happening with certain probabilities. So this is a bit different approach of computing actually than the classical computer that we were talking about, So obviously you require, now one major thing was there when Peter Shor actually in 1994 talked about that we can solve interesting problems with quantum computers. People were quite skeptical that, okay, we cannot build quantum computers because, they are quite noisy. We cannot correct errors. And the main reason for this was a paper by, a paper in Nature in 1992, which shows that you cannot clone quantum bits. So no cloning theorem was a very important theorem. So now in classical computers, whenever there is an error, so we can correct the errors by repeating the information certain number of times. So we, if you want to store information or we transmit information, say bits, we actually repeat it certain number of times, either for storing or transmitting, so that we can correct errors. But this kind of flexibility is not there in quantum computer. So it was a big challenge that people said that, okay, even if it can solve certain problems, we cannot build these machines because there are error involved in doing. Okay, and Peter Shor himself, using the clever idea of repetition, he actually now encoded qubits into an embedded space actually, and that was a very good idea of birth of quantum error correction in 1995. And it is because of this now you see a lot of development in quantum machines actually. So this error control, the idea of quantum error correction was very, very important in that sense. So there is a quantum error correction, which is very important area. In fact, I am one of the expert in that. And then there are quantum algorithms, that there are certain problems that they can solve with quantum computers. Obviously, that's a very good area. As I mentioned, quantum machine learning, this is something very hot area. You can solve many interesting problems. In fact, especially in the finance domain, many banks are now interested in that area. Okay, and so now in terms of circuits, if you say, as you know, classical Turing machine is a pen and paper machine. So we cannot do much if we want to build that machine. So basically, people discovered circuit representation of the machines, of the Turing machines, and that was really very, very important for the development of these computers. Similar thing happened for quantum computers in 1993 and also in 1995. There are a couple of papers in 1993 and 1995 which led to the discovery of quantum circuits which are easy to handle and analyze. And that is the reason, a lot more things. Now, if you compare classical circuits and quantum circuits, so there are basically many gates in quantum computing. For example, Hadamard gate, which is 2-qubit gate. There is no classical analog of the Hadamard gate. So Hadamard gate takes two qubits, and based on the nature of first qubit, it will either do nothing to the second qubit or it will flip the second qubit. So this is a very nice kind of gate which is available. There is a NOT gate which is which will flip the bits actually. So there are different kind of. So basically, one key difference between classical computers and quantum computers is the errors that they happen. In classical computers, normally we assume errors are bit flip. 0 will become 1 or 1 will become 0. Whereas in quantum computers, we have two kind of flips: bit flip and phase flip. So it's much more advanced kind of errors, and so different kind of error correcting codes are required for getting errors in quantum computing. So I think this is a general scenario. If you have any specific questions, I will be happy to answer.
Yes, absolutely. What is meant with and I've been reading that superposition is something that we find within quantum computing. What is meant by superposition? How does it play a role within quantum computing?
Okay. So basically, if I compare, say, single bit, classical bit, and single qubit. So single bit, as I mentioned, in the register is either 0 or 1. Whereas in case of qubit, it is 0 as well as 1. So basically, we say that it is superposition of 0, 1 at the same place, and many things in between, because it's a linear combination of, we are acting as a, vector space. This is the key difference. So basically, that's why we say that, in fact, that's why when we make a, computer out of classical bits, we can only say at any point, suppose we take 3 bits. So we are operating only on 3 bits at a time. Whereas in quantum computers, we can operate in all 8 bits. If you have 3-qubit register, we can operate in all 8 bits together. So it's obviously this computer will be more powerful because of this superposition nature, or because of this, because it could be 0, it could be 1, or it could be anything in between. And whenever we do the measurement, it will collapse into one of the state. So that's a really key difference.
Okay. How does this superposition characteristic, let's say, brings an advantage to quantum computing compared to traditional computing? Why is it important that we have this characteristic of superposition?
Yeah, so I think let me can I share one of my slides with you? Maybe there I can actually show you really nicely. 1 minute. Give me 1 minute actually. Yes.
Okay. Okay.
Can you see my screen now?
Yep.
Yeah, now you see that this is the classical register. You see, this is the classical register here, and this is a quantum register. You can see that here bits are either 0 or 1, whereas here there are superpositions of 0 and 1, right, at each places. So, this is kind of a sphere, which is rotating. So, if you compare 3-qubit, this is a 3-qubit thing you see here, 0, 0, 1, okay. Whereas here, all these 8 classical bits are together. So when we make computer out of these 3 qubits register, it will be more powerful, obviously, as compared to this. Because when we make a computer out of 3-bit register, we are only operating with 3 bits. Whereas in case of, because of superposition nature, when we make computer out of 3 qubits, actually we are operating on all these 8 strings together. Okay. So this gives a competitive advantage over the classical computer. In a very loose sense, I'm showing you the picture that obviously quantum computer will be more powerful because it is working on all these bits simultaneously. Okay.
Okay. Can you briefly touch on quantum gates and quantum algorithms? What are
Yeah. I think I can show you some quantum gates as well. So you see, I think, yeah, look at this here. So basically, if I take 2x2 unitary matrix, so, A is 2x2 unitary matrix. So first of all, I should say that what is qubit here? Let me show you qubit here. Qubit is, yeah, here is, you see, a qubit. Cat q is equal to alpha times cat 0 plus beta times cat 1. Cat 0 is this vector and cat 1 is this vector. Okay. This linear combination. This is a single qubit where alpha, beta are complex numbers and they satisfy this normalization condition. So whenever we are doing measurement, we will get 0 with probability mod of alpha square and 1 with probability mod of beta square. Okay. So this is a single qubit. So this is the sphere. This is the key thing, as you can see here. Okay. This vector is rotating. This is the ground state. You can say excited state. 2 states are there, any 2-level system, and this vector is rotating. So whenever we are, so basically this is our qubit. Whenever we do measurement, it will collapse into either 0 or 1 with certain probability. This is the key idea about the qubit. Okay. Now, once we have this qubit, then I can describe gates in terms of 2x2 unitary matrices which are acting on it. Okay. Any question at this point?
No, so far so good. Okay.
Okay, so now you see these are the 2 qubits. So 2 qubits can be written as cat psi is equal to alpha times cat 0 0 plus beta times cat 0 1 plus gamma times cat 1 0 plus delta times cat 1 1, where all these cat 0 0 is this vector of length 4 and so on. So basis states are this, and then we have these scalars with normalization condition that mod of alpha square plus mod of beta square plus mod of gamma square plus mod of beta square is equal to 1. Okay, this is a 2-qubit system. Similarly, n qubits, we can talk about n qubit system. This is the general n qubit system here with these things. See, whenever we are doing a measurement of n qubit register, there is certain probability we can read 1 qubit. Okay, this is first understanding about the qubits. And then we have, evolution of the qubits happens because of this normalization condition. It has to be unitary evolution. And that's why we have this these matrices. So now we have this 2x2 unitary matrix A from C square to C square. You see, this is a qubit alpha times cat 0 plus beta times cat 1. You apply A here, you get this, which is this. Okay, this is a very general unitary matrix acting on a qubit. And now there are special cases. For example, we can describe this matrix by R theta. The theta is 0 and 2 pi. And this acts like this. R theta is a unitary matrix. And you can see that if theta is equal to 0, we get I2, identity matrix, no change. Okay. And when theta is equal to pi, we get not matrix, not gate, 0, 1, 1, 0. So it will flip cat 0 to cat 1. Okay, cat 0 to cat 1 and cat 1 to cat 0. You can clearly see that, right? Cat 0 is that factor here, Cat 0 is 1, 0 here. You can see here. 1 0 here. 1 0 vector will switch to 0 1 vector because of that NOT matrix. Okay. Or if you multiply NOT matrix with 0 1, we will get 1 0. If you multiply on 1 0 vector, we will get 0 1 vector because of NOT gate. That is a NOT gate actually, right? So which will flip the bits. So this is the NOT gate. This is a bit flip. Okay, you can see the multiplication is working fine. Similarly, there is a phase flip. This gate, if cat 0 is there, it will give you cat 0. If there is a cat 1, it will give you minus cat 1. This is the phase flip. And there is a combination of bit flip and phase flip. This gate is there. There is a square root not of gate. This is a typical quantum gate. There is no classical gate here. And the Hadamard gate. So Hadamard gate is applied by taking this matrix, Hadamard matrix. 1 over square root of 2 is a normalization condition. 1 1 over 1 minus 1. You can see that these matrices rows are orthogonal and columns are also orthogonal, right? This switches cat 0 into this state and cat 1 into this state. This you can observe by just multiplying h to the bits, the cat 0 or cat 1. Okay, so this is basically a basic single qubit gate. Okay, and there is a 2 qubit gate which is control NOT described by this matrix, and this is the circuit how it is. The first bit is a control and second bit is a NOT. It will be applied or not depending upon the position of the first bit. If you look at here, cat 0 0, if you apply control NOT, because first bit is 0, there is no change in the second bit. It will remain 0. If the first bit is 0, no change in the second bit. If first bit is 1, apply NOT gate in the second, which is 1 1. If the first bit is 1, apply NOT in the second, which is 1 0. This is how it operates. Okay, this is a typical diagram here. This is the matrix. You can verify all these things by multiplying the corresponding matrices. Okay, it's really simple. So essentially, you require a little bit of linear algebra to understand these things. Okay, so this is how control NOT gate. Now I can show you circuit. This is a very simple quantum circuit. You see, there are 3 bits: cat 0, cat 0, cat 0. One Hadamard gate, one control NOT, another control NOT. So when we apply Hadamard gate on cat 0 0 0, which is this, so this will become first bit 1 over square root of 2, 0 and 1. Remember, Hadamard gate was combination of 0 and 1 here. You see, cat 0 will give you 1 over square root of 2, cat 0 plus cat 1. Right?
Okay.
So this is what is happening here.
Okay.
1 over square root of 2 this here. Then we apply control NOT. Based on the now you can see that first bit is control, second bit is NOT. First bit is 0 here, so there is no change in the second bit. Here first bit is 1, the second bit will be changed to 1. 1 1 0. Then apply second control NOT. So finally we will get this thing. This is how we operate circuits actually. Got it? This is a very simple quantum circuit involving bunch of quantum gates.
Okay. Okay. You previously mentioned the quantum error correction. Now, can I ask you to elaborate a bit on quantum error correction? Why is it relevant and why is it actually an active area of research within quantum computing?
Yeah. So now you see, simple error correction happens like this. If 0 is there, you repeat it 3 times, and 1 is there, repeated 3 times, and by majority. So if there is a 1 bit flip, suppose we send 0 0 0. So we wanted to send 0, we send 0 0 0, and 1 bit is flipped. So suppose last bit is flipped. Okay. Then we compare the distance of that 0 0 1 vector with both 0 0 0 and 1 1 1. Which one is closest? Number of places they differ. Obviously 0 0 1 will be close to 0 0 0. With the number of places they differ in that sense. Okay, so this is how we correct. But this is not possible for quantum error correction because cat psi cannot be repeated like cat psi, cat psi, cat psi. Okay, because of the no cloning theorem. And this was the major thing. And for that, actually, I'll show you the circuit also. So here is a here is a circuit basically. You see. So we have cat psi, which is alpha times cat 0 plus beta times cat 1. And then we have 2 more Ankila bits, cat 0 with control NOT here. This will prepare. So this, our qubit, alpha times cat 0 plus beta times cat 1 is now encoded as alpha times cat 0 0 0 plus beta times cat 1 1 1. Okay. So this is not the simple repetition, 0 going to cat 0 going to cat 0 0 0 or cat 1 going to cat 1 1 1. It is a linear combination actually. Okay. So this is possible. Okay. So this ensures the encoding. And then we can do the similar kind of decoding, once we send this and we do, here is a based on certain probabilistic calculation, just like in the classical error correction. So here is the complete circuit actually. This wheel part is encoder. This is the decoder. Okay, and you measure the syndrome. The syndrome will come either 0, 0, 0, 1, 1, 0, 1, 1, and based on that, we will do some action here to correct the errors. So here we send single qubit, cat0 plus cat1, and here we receive, so from here encoding, after encoding, we send cat000, alpha times cat000 plus beta times cat111, and then we do the, if errors happen, so then this circuit can correct the errors. Okay, single bit flip. Okay, so then there are different modifications. So this is the complete circuit. Okay, so these are the gates used. Single bit flip error can be corrected by this circuit, where we are sending this alpha, alpha times cat0 plus beta times cat1 is our original qubit, and we are sending after this encoding alpha times cat00 plus beta times cat11 on this noisy channel. One bit flip is allowed, and then we can correct based on these probabilities. Okay, this is a simple circuit, and in fact, this has been modified. So Peter Shor actually modified this bit flip to also phase flip. Okay, and in fact, this is a program you can write on IBM Qiskit for this. Okay, and bit flip and phase flip are conjugate to each other basically. So you can apply Hadamard gate to change bit flip into phase flip and phase flip into bit flip. So basically, this circuit can be modified. So this is the top circuit is for correcting any single bit flip. Bottom circuit is for correcting any any phase flip, single phase flip. Okay. So here, because of these Hadamard gates, we can do this. And so finally, Peter Shor actually came up with this 9-qubit code. This is so alpha times cat0 plus beta times cat1 is encoded as alpha times cat0l plus beta times cat1l. These 9 qubits are used to correct single bit flip. So this is all about quantum error correction. I'll give you some really basic underlying idea. And in fact, this was not an optimal one. One qubit can be protected by using only 5 qubits. This is an optimal code discovered by many others in 1996 actually. Even 7 qubits can also be used to protect 1 qubit. Peter Shor discovered that 1 qubit can be corrected with 5 qubits. Okay, so this is the basic idea.
Okay. Can I ask you instead, which area you believe are going to be most impacted by quantum computing? Where will we find the most, let's say, the most relevant and disruptive breakthrough thanks to the field of quantum computing?
Sorry, repeat it. I couldn't understand what you were saying. What?
Yes, so I was asking which area of research will be mostly affected by quantum computing? So which area, which domain of knowledge will have, let's say, will experience the greatest breakthrough thanks to quantum computing, where we will see major discoveries thanks to the advent of quantum computers?
Okay, so as I mentioned, the hottest area in quantum computing is quantum machine learning. Okay, and people are trying to use it for, quantum machine learning is quite hot buzzword these days because of a lot of applications in the financial sector right now. On the other hand, so basically, if you really want to solve any meaningful industrial problem, you need more powerful computers. Right now, I think the largest size computer is available from IBM is 432 qubits. And it is extending. I think people will have more. I think so. Once we go into the 1,000 qubits, or maybe in that range, we can solve certain meaningful problems. By the time we need to wait, but I hope in a couple of next years we will be having those kind of quantum computers in use. So you can solve any industry problem where actually classical computers are having difficulty. For example, as I mentioned, even in biology there are a lot of useful areas. For example, many optimization problems in industry, and many problems. For example, in computational biology, in bioinformatics, there are plenty of problems which require quantum computers. So I would say that security is also very, very important thing. In basically, quantum satellite is coming up very nicely. People are developing quantum networks for quantum internet, right? So sending secure information using photons all across the continents is possible now with what they call them quantum satellite, right? And I think India has also developed one of them, such thing, and obviously US and China are there already ahead of us. And so basically a lot of activities happening in that direction also, where actually secure information. So but because of the worth of quantum cryptography, a lot more things are happening in that area. So, at one point of time, people have said that, quantum computer, even God cannot break it, But of course, there are different ways to handle the things. But, a lot more things are happening in that area, especially quantum cryptography.
Okay.
Yeah, and communication also, quantum communications.
Okay. Do you believe that, let's say, in some research areas, the experimental validation due to quantum computers will precede the advent of new theoretical framework? Meaning, translated, do you think that quantum computers will progress our theoretical frameworks with regards to many different research areas, or do you think that we still have to go through the, let's say, sort of a pen and paper struggle in some cases?
So as I mentioned in the beginning also, see, the major drawback is the hardware, okay? And the feasibility of a quantum computer is possible only because of quantum error correction. And that technology has advanced quite a lot from 1995 till now. In fact, recently, last month or so, there was another discovery by some scientists where they are able to actually monitor the errors in quantum computers and automatically correct it. Interesting things have been developed actually. So because of that, I think more and more things are happening, and I think as I mentioned, industry is the driving force now rather than academia, and because of the industrial things, basically more and more problems will be solved in the near future, because as soon as we increase the number of qubits, one thing which was there in 2019, quantum supremacy was achieved by Google actually, so this was something really great, right? So basically that they have shown actually, with their machines. So I'm saying that more such things will happen in the next coming years, where more and more practical things will be achieved. And as soon as the number of qubits will go to 1,000 qubits, we will see a lot of things. So right now, in fact, many companies are also hiring in this area, especially in Europe. Also, a lot of work is going on in quantum computing actually, right? So both academia and the industry as well.
Okay, and which challenges or problems do we need to face before making quantum computing more widely applicable, more reachable, not only more usable, not only used by the, let's say, big companies as IBM or Google? What steps still do we have to achieve such that quantum computing will really become more widely available, not of course for every let's say in every portable computer, but at least open to some general public, at least with regards to some industries?
Yeah, so I think I think if I understand your question correctly, you are asking that, of course, big companies are using the quantum computers for solving certain problems. What about the common man, right? I mean,
whether when it will become, like, for example, like let's say translated the internet at the very beginning of the days was used not by the, let's say, small businesses, small companies. Of course, now it is. When will this happen for quantum computing?
So I would say that quantum networking is an area which is based on photons. We'll see a lot more progress for common people actually, because they can really use that product, because quantum cryptography and quantum security and quantum communication, basically quantum networking is really ahead. Actually, solving common problems with quantum computers for a common man, maybe that will be, it will take some more time. But I think quantum networking is the area where actually a lot more progress is possible.
Why do you think so?
There are governments actually which are working on these products, quantum networking. And also, in fact, in Europe also, I have seen a lot of interesting things going on. People are developing the whole protocol and things for quantum networking, so that quantum communication is possible. So essentially, I would say that probably in future you may see quantum internet based on photons, using quantum satellite. When I say quantum satellite, means satellite is using these photons to do all these things. So that might be a possibility.
Okay. Do you think that quantum computing may help us achieve new insights within our, let's say, partially and slightly flawed physical theories? Meaning, we know that our physical theories of quantum field theory and general relativity, they break down, for example, within a black hole singularity. Do you believe quantum computing may help us? And of course, we have many other unsolved problems, open problems in physics. Do you think that quantum computing may help us addressing these problems?
Actually, I would say that it is because of the birth of quantum computing, a lot more progress has happened even in quantum physics also, and people who understood the quantum physics in a much more better way because of quantum computing. And in fact, there was a very interesting paper by John Piskel recently, where they talked about space-time. So they say that space-time that we use, or in the black hole, actually, quantum error correction is working actually there, So it's interesting connection. So basically, when we want to understand nature, in that sense, also quantum computing is going to play a very important role, because you see, nature is processing information, and there is a very nice book by S. Leroy from MIT about this programming the universe, where he talks about that the universe itself is a quantum computer, So in that sense, also, apart from the practical uses, one will have much more greater understanding of the universe as and the theoretical science more, how things are working in the nature, And in fact, there was a model by Stuart Hameroff and Rosa Penrose. Rosa Penrose is a person who received Nobel Prize recently, right? So in fact, I interacted with them in 2003 in a quantum mind conference, and there they proposed what is known as quantum computing inside the brain. So they say consciousness is also because of quantum computers. Okay, so they say that inside our brain, there is a protein tubulin which can act into two states, alpha and beta, and act as a qubit. And it is because of this quantum computation. So there is a model. Of course, there are a lot of controversies also in that model, but obviously, all these new ideas, they're saying that the consciousness is because of quantum computer inside our brain. So so it's really interesting thing. So I think that also photosynthesis can be explained much better using quantum computers. Other things, people have discovered that even the migrating birds use quantum algorithms to find their path. So different time when we combine nature and quantum computing, a lot of interesting avenues are there. Apurva Patel from ISC Bangalore, he has written a paper and arguing that we have 4 nucleotide bases ACGT and amino acids, 20 amino acids inside our DNA, because 20 amino acids inside our in the protein, because of the quantum computer, quantum algorithm is sitting there. So a lot of such interdisciplinary things are happening, and many interesting ideas are emerging actually. And so certainly a direction is there for quantum biology, which is very, very, there are a lot of books. In fact, I have written a review paper in 2006, The Quest for Error Correction in Biology, where I talked about some of these initial ideas, how error correction is involved in biology. And of course, quantum computing also plays an important role there.
Okay. Yeah, I understand. I would like now to move on to DNA and DNA computing. You mentioned before about error correction methods, but we know that we can also find error correction methods not only in quantum computing but also in DNA computing. Can you firstly explain what do we mean with DNA computing? Because we all know what is DNA, but what is meant with DNA computing, and how do we exploit this type of computing?
Yeah, so first of all, let me tell you brief history. DNA computing was also started in 1984. In fact, 1987, theoretical idea was there, but actual experiment was done by Edelman in 1994, where he took a instance of Hamiltonian path problem and solved it using bunch of DNA strings. Okay, this was a remarkable discovery. It was a science paper, and okay, so now what do you mean by DNA computers? So our problems can be solved by a bunch of DNA strings interacting with each other. So two DNA strings, ACGT, can combine each other by complementary base pairing. For example, A is complement to T and C is complement to G. Okay, there's a hydrogen bonds in between. So this hybridization is backbone for DNA computation. Right? So whenever we, so we need to find. So whenever if we want to use DNA computers, we need to find a way to convert our problems into a bunch of DNA strings, and those DNA strings interact, and finally you can read out the solution. So there are different mechanisms through which this can be done. And in fact, as I mentioned, the Turing thing is a very, very important thing. For just like that quantum Turing machine came in 1985. Similarly, Eric Winfrey at Caltech has shown that it is possible to do universal computation with DNA computation. So essentially, he talked about the idea of algorithmic self-assembly. So self-assembly is very common process that we observe in the nature, and self-assembly of DNA can give rise to all four machines in computer science. So it's a really interesting thing. So essentially, with earlier people were doing computations with DNA from a trial and error method, but now there is a more systematic approach, more programming approach to do the things, and some of these basically things can also be implemented with what is known as dynamic strand displacement, DSA. So bunch of DNA strings, we call them dancing DNA. DNA strings are interacting with each other and solving a problem for you. That is a possible. People have built even logic gates using these kind of DNA strings. All kind of computations are possible. So there is a whole bunch of DNA circuits. Okay, and very recently in 2012, another branch of DNA computing has emerged, which is known as DNA storage. So we can store data on DNA, and this is something really very, very remarkable. This work was started by George Church at Harvard, and since then a lot more activities has been there, and now there is an international consortium of DNA Storage Alliance, which is let me show you, I guess, quickly maybe some slides here so that yes, you can see here. So basically, so these are the different branches of what is known as biomolecular computing: DNA computing, RNA computing, membrane computing, peptide computing, and bacterial computing. So out of this, membrane computing and peptide computing are more theoretical. Peptide computing with proteins, membrane, cell membrane, okay, RNA computing, but a lot more work has been done on DNA computing and bacterial computing. So we have done a lot of work because these are more experimental also, so DNA computing and bacterial computing. Okay, so this is the overall broader classification. Okay, this is the self-assembly of DNA, and you see this is a comparison with classical computers and the DNA operations. So there are certain DNA operations that you can do on the DNA strings. Okay.
Okay, can you let's say elaborate a bit about both DNA computing and DNA storage, data storage later? But how does let's say, how do we store data thanks to DNA? How do we exploit the properties of DNA to achieve a more efficient computing method?
Yeah, so actually I should say that first of all, DNA is a very mature way of storing data because nature is also using for storage purpose as well. And 1 gram of DNA can store 455 exabytes of information. So 455 exabytes in the order of 10 raised to power 18. Now, how much information is this? If I ask you that, if you compare that, what is the size of internet? So roughly, we say that it's about 700 exabytes. So 2 gram of DNA can store entire internet. Okay, and 1 kilogram of DNA, 1 kg of DNA can store any information ever produced on this planet. So it's the ultimate storage density that we are getting with DNA storage. Okay, so this is something. Now, obviously, there is always, again, whenever we are sending information from one place to other place, means communication or storing from now to then, we require error correction. So error correcting algorithms are going to play a very important major role everywhere. Okay, so that's where I think my role also comes, because I am an expert in error control algorithms. So we work on different kind of error correction techniques when we want to store data into the DNA. So I think, let me see if I have. So these are, by the way, these are the branches, or different branches of DNA computing: DNA nanostructures, DNA ties, DNA strand displacement, DNA circuits, DNA storage, and DNA cryptography. So I think we are working in almost all these areas. So let me show you some. Yeah, this is the chemical computing, by the way. This is another area, DNA origami, which is also coming as, yeah. Yeah, here is a picture. You see, now you see here in this picture, you can see that first you encode the data by testing into ACGT. Then there is a synthesizer. These are machines which are standard, which will convert into the physical DNA, and that you can store in the test tube. Then you can retrieve the test tube and do a sequencer machine, which will read the data, and then you use the software to convert it back to the media file, whatever it is, PDF, doc, image, movie, whatever you want. So this is a typical scenario for how DNA storage works actually.
Okay, what properties of DNA can we, let's say, do we really exploit to achieve this high performance characteristic that DNA gives us, provides us for computing and storage?
So I think, as I mentioned, in the case of DNA computing, there are different directions right now. One of them is, which is very popular, is DNA origami, as I mentioned. So origami means you can fold the DNA into desired shape. Okay, and that can be used for drug delivery. You can make some small box where you can put a drug molecule and inject it inside your body, which will transport the drug, right? That is possibility, and there are different kind of other applications are possible. Now, basically, in terms of storage, right now, most of the people are working about basically one-time or archival storage. Okay, because readable storage, there are a few challenges. Some work has been done, but still some work is going on. But archival storage is really important area, because I think even in terms of storage, if you look at often out of 100% data, we only use, so I think I would say that 70% data is cold data. We don't access them quite often. So we only access 30% or 40% data, which is known as hot data. Okay, so all this cold data can be stored in the archive. Okay, so whenever you require, if for the large density things are possible. So that is a really interesting thing where people will be able to do things, So this, you see, this is the letter and the corresponding DNA strings are there. I'll show you I2T2 text encoded into the DNA string. This is similarly for the image and so on and so forth. Okay, and I think these are the founders, Emulia, Microsoft, which buses in Western Digital. I think there are about 44 member organizations which are working on developing the standards. I am part of it actually. Our lab is part of it. We are developing the standards for DNA storage right now. Okay.
Okay. What are let's say the main or actually the let's say the hottest area of research that can be affected by DNA computing? Where does it have the most useful and helpful applications?
Yeah, so as I said, DNA storage is something really very useful application immediately. DNA origami is also another very useful application, which is developing a lot of even there was a vaccine based on DNA origami has been developed last year. So even there, see, when we talk about DNA computing, means we are actually controlling DNA in our desired fashion, and that's the main purpose. Okay. Whatever we want, we can do with the DNA actually. So that is something is giving us plus point there. So these two areas are immediate use. Obviously, people are doing things in the lab, trying to develop different things. But practical purposes, these two areas are very, very important. DNA storage and DNA origami. Where certain vaccines can be done or drug delivery systems can be designed using DNA. Those are the two popular areas of DNA computing.
Okay. And let's say what are some common error correction methods used in DNA storage?
So in terms of error correction mechanisms, first of all, you should know that classical error correction, normally we do bit flip, right? And in quantum, we have bit flip and phase flip together. Whereas in case of DNA, we have different kind of errors possible. And one of them are, insertion, deletion, or substitution of bits. Basically, ACGT could be inserted, deleted, or substituted. Okay, so you will kind of flip. So basically, different error model is there. So different error correcting codes are required. So a lot of work has been done on these DNA codes. So basically, we want to design bunch of DNA strings which are sufficiently dissimilar to do the computation for you. Okay, whether it is DNA origami or DNA storage or any other applications. So a lot of techniques are available. So we essentially construct a bunch of DNA strings with certain combinatorial and thermodynamical properties so that they are useful for applications.
Okay. Let's see what are the most common methods, the most common error correction methods.
Yeah, the most common is, I think, I would say that there are, one of them is yin yang codec, which is actually, I would say that. So of course there are many mechanisms, but yin yang codec is very, very important because it has achieved this physical density, close to physical density, about 432 qubits. So sorry, 432 this exabytes of information in 1 gram of DNA. That is achieved by yin yang codec, which was discovered by again George Church last year. So this is something very, very important. Okay, and apart from that, people are trying different classical. So they are actually trying to generalize different classical techniques to the DNA storage area. Okay, so we have different kind of techniques actually. Almost we have the Hamming code also. All other different techniques are there.
Okay, you also deal with let's say you also work in coding theory, right? Can I ask you? Yeah, can I ask you to elaborate a bit on what is coding theory and how does coding theory relate to error correction methods used in, for example, DNA data storage or more in general error correction methods?
Yeah, so I think I can again show you 1 or 2 slides here. Here is the error correction thing. You see. You see, this is the basic error correction. Okay, so this is the thing. Coding theory is of 3 kinds: source coding, when we do the data compression; channel coding, when we are actually sending information or transmission. So normally, and we have the third case is joint source and channel coding. So we have codes for doing all these three, operations. So we have a message source. We encode the data and send on the noisy channel. We receive it, decode it, and then use it for our purpose. So this is a channel coding thing. So we have done. So I have worked, especially in my PhD. I have constructed codes over finite rings. So it's another interesting area. Which was more theoretical at that point of time. But the work that I have done, I have constructed the Hamming codes and simplex code over finite rings, especially integer modulo p raised to power s, where p is a prime. And apart from after that, as I mentioned, I have done work on quantum error correction. So we have done some work on. So basically, these quantum error correcting codes have some connection with finite geometry. So we have looked at some of those connections earlier mathematically. And then we have also, in terms of DNA storage, we have some of our own techniques for correcting different kind of errors in DNA storage, for example. So these are some of the areas where we have done some work, especially from the coding theoretic point of view. Okay, so normally, how do you construct codes? It requires some combinatorial mathematics, algebra, algorithms, and some application. So bottom line is use redundancy in a clever way, so that you can minimize the resources. Whenever we are repeating the bits, but you should also know minimum repetition so that we can correct maximum errors. That is a bottom line, okay, for correcting the errors.
Okay. What are some of the let's say major open problems within coding theory?
Yeah, so basically, coding theory has vast applications depending on what kind of channel we are looking at. If it is deep space communication, data storage, I think, for example, if you look at your pen drive that you use, that also uses error correcting algorithm inside. Okay, your hard disk uses this kind of mechanisms, error correcting algorithms. Hard disk, satellite communication, power line communication, diverse applications. Actually, I would say that. So whenever we are processing information in any form, whether it is classical computer, quantum computer, we are sending information from one place to the other place, or we are storing information from now to then, we require error correcting codes because errors are bound to happen. Okay, this is in fact observation by von Neumann. So basically, you need to have some sort of error correction algorithms. And bottom line is this: we want to have optimal error correction techniques, which uses minimal resources to correct maximum errors, whatever is possible. Okay, so there are different popular schemes like Hamming code, read-only code. VCH code is very, very important code in the classical coding theory, both of the program code, VCH code, which is very engineering friendly. So depending on how many errors you want to correct, you can design the code actually for correcting errors. And your CD, hard CD, DVD, all these devices have error correcting algorithms at the back end. It's a very, very important area for research as well as for mathematicians, and also applications in computer science, now even in biology, everywhere.
Okay.
Yeah.
Okay, amazing. Okay, so we just passed the hour. I think we can wrap it up here. It was very interesting to to learn all these geek topics. It was very interesting. So thank you very much, Manish, for your time and your availability and your explanation. And yeah, it was my pleasure having you. So thank you again. And I want to thank everyone for following along with us. This was the 14th episode. You will find the website of the Gupta lab Manish. I will attach. I will link to the video, and so you can check his work and his research areas.
Thank you very much. Yeah, I hope some students will find it useful and they can attract towards this area, and they can, even some mathematicians will find it helpful.
Absolutely.
Thank you very much.
That's our hope. So thanks everyone for following along with us. I will see you in the next episode. Bye.
Thank you.